Okay, good morning. Um, Hope everybody's doing well, and that you're ready to go. Yeah, I had my first cup of coffee already, so I think I have enough caffeine, enough that I'll be good to talk to you a little bit about energy conservation. So, let's see. Does anybody have any questions before we get rolling? You guys doing all right? Appears to be a little bit of a gloomy day where I am. Kind of rainy so far. Yeah, maybe it's almost better, I feel like, when we're stuck inside, if the weather outside is kind of crappy. That way we're not, it's, it's not taunting us by being nice out. So, yeah, a little gloomy. That's all. It's all good. We'll be all right. We're getting there. So, I'm excited to talk to you today about energy conservation. We had a lot of problems with uh, just, I had problems with my pen on Monday, and I got some new batteries for it. So I think hopefully, knock on wood, that will be better behaved today. And instead of just talking about these ideas in abstract, we'll look at some example problems to kind of show you all the things that we've mentioned so far. So let's go ahead and get started. So energy conservation. Um, Conservation laws are a pretty common thing in science, in physics, and I would think of this as if something is conserved, it's neither created or destroyed, it's kept the same. Oh, hello, Carolina. So it may be transferred from one form into another. Um, like that's basically the theme of energy conservation in the way the chapter is presented in your book as well. We can have energy that's in one form and convert it into another form, but the total is going to stay the same. It's conserved. So I suspect you've maybe seen something similar with, um, like in chemistry, maybe conservation of mass. Like you're not going to lose uh, material, lose atoms or anything, but you could transform from one compound into another or something like that. Um, and I would say, we're just going to talk about mechanical energy. So we talked a little bit about this in lab if you have lab yesterday. But to start, mechanical energy, um, which is just the sum of potential energy and kinetic energy. And just recall potential energy. So far, we've basically been thinking of this as mgh with regards to, well, here, let me be a little more thorough. Potential energy, there's basically two kinds that we're going to work with a lot. Gravitational potential energy, which is basically mg delta y, and the potential energy stored in a spring, which is 1 half kx squared. Um, and kinetic energy, recall, we introduced this at the end of the last chapter, is 1 half mv squared. So we have sort of these ingredients, and conservation of mechanical energy will mean that the total amount of potential and kinetic stays the same. So a lot of problems will consist of converting something like potential energy into kinetic energy. And we'll look at some examples of that today. Um, And then a couple other things. There were a couple more mathematical relationships that we made use of, or we introduced last time. So one is the fact that, so I want us to have an opportunity to practice. I'll show you some examples of those today too. So one is that the potential energy is given by the negative derivative of the force. So really this is the negative work, and actually just for consistency. Sorry for kind of swapping between two different. Let me just put this up here. Your book uses the capital letter U for potential energy and K for kinetic energy. I tend to just use PE and KE because I think it's unambiguous what those are standing for, as opposed to U, which is not, doesn't really immediately tell me what it is, I think. So potential energy was the negative work, and that was given by the negative integral of a force. And we looked at last time, I think, examples including, gravity and the spring, and that's where these things came from. And so this relationship is one that gives us an opportunity to practice our calculus skills, because if we're given a force, we can find the potential energy due to that. And then there's sort of a complementary thing here, which was the fact that the force, so this would allow you to transform from a force into a potential. We can also do the situation where if we're given a potential, we can transform it into a force. And we do that by taking the derivative of the potential. And so let's first look at a couple examples, just to give you a flavor for how you go about doing this. It gives us an excuse to practice a little bit of calculus, and it will also be useful for the homework that's associated with this. So, as an example, let's see here. So, check out this problem. So, we're given a potential. Whoa. Negative ax over the quantity b squared plus x squared. And we're told that a and b are constants. So we want to know what is f as a function of x. So to find this, we're going to use this definition that I just put up there. How we would do this is we would take the derivative of this. So let's do it. F of x is going to be the negative derivative. I think folks are pretty comfortable with derivatives. So we need to take the derivative of this function. So the way I suspect you've learned this quotient rule, the way I remember how to do this, it's kind of cheesy, but it's going to be the top high, d low. So, and what's the derivative of b squared plus x squared? Well, that would be b squared will be a constant. Wait a second, I'm doing this backwards. Low, d high. So the derivative of this would just be negative a minus high, d low. So the derivative of the numerator here, this would be a constant. We'd pick up a factor of 2x. all over the square of what's below. And so we can expand this a little bit. Notice, let's see, we would have a term that's negative b squared a. I'll just write it out just so we have for completeness here. We would have a term that's negative ax squared. We'd have and then a positive a positive 2ax squared all over that same denominator. And so notice these two terms we can combine. So when we consolidate that, we would have 1 factor of ax squared minus this remaining b squared a piece. Okay. And still over our b squared plus x squared, quantity squared. And we could, we could factor this factor of a out of the numerator if we wanted to, and we'd be left with x squared minus b squared over b squared plus x squared, quantity squared. And notice, remember in our definition of finding the force, we need to take the negative derivative. So I've taken the derivative, but really there's, I neglected this negative sign. So let's make sure to incorporate that. That's going to switch the signs here. So let me just change this. So this would become positive b squared negative x squared. And then this would be our final expression for the force as a function of x. So, like I said, this gives us an opportunity to practice our calculus. Even for me, this problem in particular is an excuse to brush off the quotient rule. So I don't know what how you remember that, but yeah, like I said, the way that I remember it is low d high minus high d low all over the square of what's below. It's kind of cheesy, but it has stuck in my brain for about 20 years now. So questions on that? Do you feel comfortable with that kind of problem, doing simple derivatives? So in this case, I think it's kind of cool. You've seen problems like this, I suspect, in calc that are identical to this, but we're using this to actually find something where we can relate force and potential energy, which is pretty cool. Questions? All good? All good? You're like, blah, we know how to take derivatives? Okay. So I also want to give you another, yeah, so it does. And I did. I kept it outside here, or basically I forgot to incorporate it until the end. And then I made sure that it was incorporated at the end and it switched the sign of this. You can do it however you want. I would recommend you do it however works for you. This, as you know, doing problems like this, and probably you've observed in the homework system too, negative signs are, uh, missing sign is probably about the most common thing that can trip you up. So I'm not going to tell you to do it one way or the other. I think it's something that you kind of need to come up with what works best for you. I did it that way because I was in the mindset of like, well, I'm going to take the derivative and then I'll deal with the negative sign. But you can distribute it in there and then take your derivative. Either way would be fine. Okay. So the other calculus relationship that we wanted to take advantage of is the integration. And I think integration, of course, is a little bit trickier maybe than uh, differentiation. So this problem, a particle is constrained to move in one dimension, is subject to the force f of x that varies with the position as f of x. Oh, I should mention, this is implicit here that this is an I hat. Remember, we've transformed between, I wasn't very diligent about that, but let me just say, this is implied that this is in the I hat direction. But recall, what we've done here is we've transformed between energy, scalar, to force, vector. And now we're doing basically the opposite. We're going from force, vector, to energy, scalar. And notice this has a direction associated with it. So anyway, a particle is constrained to move in one dimension is subject to the force f of x that varies with position as f of x equals a sine kx, where a and k are constants. And we want to know what is the potential energy function, u of x, if we take u to be equal to 0 at the point x equals 0. So what this problem is asking us to do is convert from force to potential. I'll just call this whatever label you want to use. And the relationship for this was that we need to take the integral of the force.dl. Now, this dot product, it's basically assume that we're going along the x-axis. This becomes negative a sine kx dx. Okay. In other words, we're not trying to do both the dot product and integration at the same time. We're looking at the slightly simpler, the simpler case where we're just concerned with the force and the displacement that's along the same direction. In other words, they're aligned, if you want to think about it that way, such that, f dot dl equals f dx. Okay, so I like this question because this gives us an excuse to exercise another common function that you should be able to work with, and that is sines, or sines and cosines. And so we need to take the integral of sine of kx. So notice if you have a constant, the constant's not going to matter. We can be really explicit about this. Let's pull the constant out. Oh, and we should say, let me be, yeah, just really explicit. So the integral is not going to depend on the constant, so I can pull it out of the integral from underneath the integral sign. Um, and so we need to take the integral of sine of kx. So the integral of sine of kx would be negative cosine of kx over k. And you can check so if you're less comfortable with integration, you can always check your work here by quick taking a derivative. So the derivative of cosine is going to be negative sine. So if it's negative sine, we pick up the sine, and then you'd have to take times the derivative of the argument in here. You'd pick up a factor of k, so that k's would cancel, so you would recover the sine kx, and so we would get back to where you started. So this gives us confidence that this is the right integral. And notice this is indefinite, so this is a function. There would be an implied constant here, c, or I think we'll just call it c because that's the kind of the convention. And then so we have our function, but we can use the boundary condition to figure out what the constant is. So in other words, we need this thing to be zero at x equals 0. So let me put it this way. In order for the potential energy to equal 0 at x equals 0. So let's see what happens here. If we put in x equals 0, this is going to become cosine of 0. What's the cosine of 0? 1. So this would become a over k plus c. So let me put it like this. Potential energy of 0 is going to equal a over k. So this cosine kx would become, cosine of 0 would become 1. The negative a times negative, so that negative will cancel. We'll have a over k plus c. So if we want this whole thing to be 0, that means that this constant is going to have to be negative a over k. Okay. And so our complete energy function, potential energy function, would be a cosine kx over k minus a over k. Okay. So this is a pretty straightforward example, but it lets us practice a couple things. So integration. I'll just put it here. This lets us practice integration, sines and cosines. And also boundary conditions. So like the problem above, it's a good an opportunity for us to exercise our calculus skills a little bit. So I just wanted to make sure you saw examples of both of those operations because it appears in your homework. You can kind of have it on your radar. Questions about that one? I suspect, have you seen stuff that's similar to that? In calc, probably? What do you think? Pretty pretty familiar. Part of my thinking with going through a problem like this, in detail too, is that I know different folks are kind of at different points with their calc classes. So for those who are in, Calc 3, have seen this all before, it's kind of like, okay, I get it, I've seen this before. But for folks who that is new or less fresh, you have an example in front of you. It gives you a sense of the kinds of functions. So I guess I could make a pretty general statement here. For PH2011, the kinds of functions that you need to be able to do. Oh wow, can we? Yes. Yep. We'll look at a spring shortly here. Yeah, that's on the agenda for today. So the one other thing I would mention, I think one of the things that students get kind of intimidated by with regards to calculus and what they need to know for 2011 is they're thinking like, oh man, do I have to know how to integrate and take derivatives for like every function under the sun? And the answer is no. I mean, you can get a long ways with just functions like x to some power and sine theta, cosine theta. Like those functions are the vast majority of what you need to be able to use. So if you're proficient with derivatives and integration for those functions, you're in good shape. Just to kind of put you at ease if you're wondering like, what do I have to know, how to do every kind of possible function. Okay, it sounds like you guys are pretty good. Let me know, or don't hesitate to contact me if there's stuff with regards to calculus that's causing you some anxiety. We can talk about it. Um, Reduction. I'm not actually even sure. Oh, no. You mean where you would do like a substitution or something? Most likely not. No. It'll be pretty straightforward. What you see is what you get. You're not going to have to use special, you know, techniques to say transform a function, or like if I recall, there's lots of approaches where you can like transform complicated trig functions into use rules to transform them into things that are easier to integrate, for example. Don't sweat that. It's all you're not going to have to do that. So okay, that is sort of these are just like foundational skills. So let's look at some things that are uh, more relevant or more directly applicable to energy conservation. So, and just to refresh your memory, when we're talking about energy conservation, basically the energy initial is going to have to equal the energy final. And for our purposes so far, we're just talking about kinetic energy initial plus potential energy initial is going to have to equal kinetic energy final plus potential energy final. And this is what I had identified as mechanical energy. So, and this is basically section 8.3 and 8.4 in your textbook. So, let me show you a really simple example, and then we'll look at one that's a little bit harder. Okay, so here's a question for you. So after a particularly trying time with Microsoft Excel, a student drops their computer out of the window in the local lounge. The lounge is on the 12th floor. Each floor is approximately 4 meters in height, and the computer has a mass of 1 kilogram. We want to find the potential energy the moment before the computer is dropped. We want to find the kinetic energy uh, immediately before it hits the ground, and we want to find the speed when it hits the ground. Okay, so this is a question we have solved this kind of question before. You recall you can solve this with kinematics, right? Way back in chapter 2. This is another way. So I had mentioned this, I'm sure, but it's pretty satisfying and cool how as you learn more physics, you get more tools, you have more ways to solve problems. You can both solve more kinds of problems, but also you'll have more and sometimes more intuitive ways to, uh, yeah, so more intuitive ways to maybe set them up, approach them. And so, yeah, immediately before it hits the ground, that'll be right when height is 0, essentially. So basically, let's draw a little cartoon. You know, we have a building, computer goes out the window. This is the height of that window. And let's see, so we're saying it's on the 12th floor, and each floor is 4 meters in height. So we're going to say that this height, initial height, is 12 times 4 meters. And the computer has a mass of 1 kilogram. So, and we want to know basically potential energy here and the kinetic energy here. And I'm going to set this up with both being, you know, kind of extra just explicit and show kinetic energy plus potential energy initial is going to equal kinetic energy final plus potential energy final. So one thing I would mention, potential energy, and if you were in lab yesterday messing with where we were analyzing the potential energy for free fall for our lab data from lab 1, this potential energy is sort of arbitrary, but you can make in that it depends on where you choose your height. So let me just say here, potential energy depends on your choice of, let me call it y equals 0. So what I mean is that you could say that the ground has some height. In other words, you could put your coordinate system down here, and you would find that the potential energy final would not be 0, but the potential energy initial would be increased. And when you go and crunch your numbers, you would get the same result for the kinetic energy. However, it's often easier to be kind of strategic with where you pick your coordinate axes, or your origin for your coordinate axes. So for a lot of these problems where you're dropping an object and stuff like that, it makes a lot of sense to pick your coordinate system so that the y equals 0 is the ground. Because that way, when you go to set up the problem, the final potential energy, if when it hits the ground, it has 0 height, this will go to 0. And we probably kind of already had this in mind, but I put it in here anyway, so I could say, you know, the kinetic energy, if you're dropping the object, you're not imparting any initial velocity, so it has no kinetic energy initially. So we're just relating potential energy initial to kinetic energy final. So for part A, the potential energy initial will just be mgh. So it'll be 1 kilogram times 9.8 times our 48 meters. So this will be 470 joules. And then for part B, we know that this potential energy initial is going to equal the kinetic energy final. So in other words, the kinetic energy final is going to have to equal 470 joules as well. Okay. And for the last part, we can figure out what that speed is by noting that the kinetic energy final is going to equal 1/2 mv squared. So if we know that this is equal to, we know what that number is. So we can solve this for v. We pick up a factor of 2, divide by a factor of m, times our 470 joules, take a square root of the whole situation. So we would find that the velocity is, oh, wait a second. Yeah, that would work. Alternatively, we could, relate it here and notice that since the kinetic energy is equal to the potential energy, we could relate this to, let me just present this another way here. So this would give us our 30.7 meters per second. Alternatively, we could say, hey, the kinetic energy is going to be equal to the potential energy initial, mgh. Notice this allows us to cancel the mass, and so it gives us a little bit different expression, but should give us the same result. Okay, so like I said, this is another way to solve the same kind of problem where you drop an object. How do you feel about that one? Is that fairly intuitive? I suspect that if you've messed with energy conservation at all, this is basically the kind of problem that you would first encounter. So, questions about this guy? Let's see. Yeah, okay. Yeah, like I kind of suspected. If you've seen any of this sort of stuff before, this will probably be or likely be familiar. Any other questions or concerns with this one? Okay, it sounds like everybody or folks are pretty comfortable with that. Let's look at a harder example. So a harder example of mechanical energy conservation. So again, we're not talking about any dissipative anything, no friction or anything yet, although we'll look at that next time. But what we want to talk about now is a question where we have a spring. So I think Caleb was asking about springs. So this is a good question because it's definitely a little more complicated. So two kinds of potential energy. A ball of mass m equals 2.6 kilograms is starting from rest, falls a vertical distance of 55 centimeters before striking a vertical coiled spring, which it compresses an amount y equals 15 centimeters. Determine the spring stiffness constant of the spring. and assume the spring has negligible mass and ignore air resistance. And we want to measure all the distances from the point where the ball touches the uncompressed spring. So the origin for our system, in other words, is here. Okay, so energy conservation, the same starting point. So this should become comfortable for you, like Newton's laws were hopefully, setting up Newton's second law was hopefully comfortable by the end of working a lot of force problems. These energy conservation problems, your kind of comfortable starting point is that the potential energy initial plus the kinetic energy initial is going to have to equal the potential energy final plus kinetic energy final. Now, this problem is more complicated for a couple reasons. For one, we kind of have 3 locations instead of just 2. And also, we're working with both gravity and springs. So one way we could approach this would be to kind of break it into chunks. So in other words, we can find the kinetic energy immediately before it hits the spring, and then relate that kinetic energy to the potential energy that will be stored in the spring at the end. So let's kind of do it in steps. So from 1 to 2, the potential energy initial, if it's dropped starting from rest, there will be no kinetic energy initial. Man, what is going on here? So, and then potential energy final, why don't we just call this potential energy 2, or how about at 2, kinetic energy at 2. So the potential energy at 2 will have no potential energy. It's immediately before it hits the spring. But the kinetic energy there, we will have kinetic energy because it will be moving. And you can kind of see they've given us some little helpful indicators there that it's moving. So, okay. So that would allow us to relate mgh to 1/2 mv, basically at 2 squared. Okay. So we could use that and we could pull out the velocity. But what are we ultimately after? We want to know the spring constant. We have to know what's going on with from 2 to 3. So from 2 to 3, what's that going to be? Well, we'll just be really kind of explicit about this. So looking at the potential energy plus kinetic energy at 2 is going to have to equal the potential energy at 3 plus kinetic energy at 3. And notice there's not any potential energy at 2 right before it hits the spring. Which we already made, we already noticed. And then there's not going to be any kinetic energy at 3 because it's going to have come to rest. So this will be 0. These are all 0. So this gives us a relationship between the kinetic energy at 2 and the potential energy at 3. Now, notice that the potential energy initial equals kinetic energy at 2. Kinetic energy at 2 equals potential energy at 3. So we can string these all together also. Potential energy initial equals kinetic energy at 2 equals potential energy at 3. So I suspect you may have been like, yeah, I see that already, but I just wanted you to see that we can break that down into pieces like that if we want. And sometimes for problems, it's easier to think about it kind of step by step than it is to go immediately from potential energy, or the um, energy in the initial configuration to the final configuration. Okay, but what we do need to do is state the express the energies. So the potential energy initial, mgh. The potential energy final. So here, actually, let me just let me write this over here. So what we're going to do is we're going to skip the kinetic energy piece for the time being. We can come back to that. And we're just going to state the potential energy initial and the potential energy final. So this will look like mgh. That's going to have to equal. Now, the distance from 0 for the final position is negative y. So the potential energy for a spring is 1/2 k, the displacement squared. So you can think of this as negative y squared. And actually, let me be careful. Let me make this a capital Y. In other words, it's, this distance. Notice the spring doesn't care about the sign of that because you stretch a spring one way or you compress the spring, an ideal spring that is, you're going to get the same amount of energy. That's to be distinguished, though, from the energy due to gravity. So notice the spring is doing something here, but gravity is also doing something. So in the gravity piece will be mg times the height, but the change in height for this is going to be negative y as well. So actually, let me add a step here just to be more explicit about it. This potential energy initial is just due to gravity. It's going to be converted into potential energy stored in the spring, but also potential energy that's going to go into gravity. So notice this additional distance going down is going to have a gravitational contribution, and that's what this is. So we now have an expression that relates the height, the initial height, the final position, negative y, and what we were after ultimately was k, so we can solve this thing for k. mgh minus mg negative y, so actually this would become plus mg y. That's going to equal 1/2 k capital Y squared. We can divide by a factor of y squared, multiply by a factor of 2, and actually we can pull out a factor of mg from the numerator. So this would give us our expression for k. We can put all our units in. So let's see. The mass, 2.6, 9.8. The height, h was 0.55. Y was 0.15 divided by 0.15 squared. You crunch all those numbers, you find that k equals 1590 newtons per meter. So, and recall, the units for this. The spring force is negative kx. So k must have units that convert an x into a force. So that's newtons per meter. Okay, so questions. So let's see. Carolina has a question. Why is potential energy at 2 equals 0? Because the origin of our coordinate system, yep, Caleb, is so that y equals 0 at that position. That's an excellent question, and thanks for pointing that out. I don't remember the number of the homework problem that this is like, but there's definitely some that involve springs. So questions on that? The one additional thing that we can look at is, suppose we wanted to find the velocity here in the middle. You could do that. You could solve you could get velocity. If you solve mgh equals 1/2 mv squared, notice it's not going to depend on the mass. You would find that the velocity is root 2gh, and if you crunch those numbers, that would be 3.3 meters per second. So just as sort of a side note. But notice we didn't actually have to find this to find the configuration at the end. Okay, so yeah, we will talk more about systems that have friction tomorrow. That's kind of the next. Those are of course more complicated. And then yeah, and the incline is definitely more complicated. But tell you what, I don't want to. I want to respect the time. But so next time, we'll incorporate friction, dissipation, the short story to help you for approaching those problems. Basically, the thing is that if you look at the mechanical energy before and after, and you find that there's some energy that's missing. So in other words, potential energy initial plus kinetic energy initial is going to equal the potential energy final plus kinetic energy final. But if these are less than these, then there has to be some energy that's been lost. Not lost, but energy that's been converted into stuff that we can't quantify like this. And so that will go into work that's done by non-conservative forces. So to those questions that have friction, basically if you incorporate the work that's done by friction, that allows you to solve them. So we'll look at some examples, but hopefully that kind of gives you, a sense of where you go, how you go from here. So, yeah, basically, if there's energy that's not accounted for by the mechanical energy, then there must be some work done by non-conservative forces. Friction, drag, etc. Heat, you can kind of imagine it's gonna go somewhere where we can't express it as potential energy or kinetic energy. So hopefully that gives you some tools that you can use. Yeah, sorry, our lecture last time I had problems with the pen, but it seems to be working, so I guess it was the battery. Questions? So yeah, you can start, read chapter 8, really the rest of chapter 8. So we're not going to have a quiz until it would be like a week from now. Because you have to be able to have the homework done. I don't want to like give you a quiz without you having a chance to really look at the homework and have time to ask questions and reflect on it and stuff. So, but that's a good question. Other questions? If there aren't any other questions, have an excellent day. Uh, no, of course, if you run into issues with the homework, contact me on Teams or on email or something, and we can set up a time to talk about it. Um, any other questions? Okay, well, I will have an excellent day. We will see you tomorrow.